Let's take a concrete problem of Ampere's law. We're going to be looking at trying to find the tangential magnetic field everywhere in space due to this current distribution. So just to be clear what's happening, there is no current. Well, we'll come to that later, but there's some current here which we don't know. But right now let's focus on the coaxial part. This is unknown current which we'll find in the end. But right now, inside this, if you remove that wire, inside this there is no current. In between A and B, there is a current given by the current density A times R, where A is some constant. This A is not amperes, it's some positive constant. Where A is less than or equal to R, less than or equal to B, just tells you that this current density only exists in the shell. Outside the shell there's none, inside the shell there is none. Okay, so how do we proceed? The basic steps for Ampere's law are always the same. Always use a sensible Amperian loop. Ampere's law is true for any loop. Now, of course, if you want to make your life very difficult, you're more than welcome to use a loop that's impossible. But a sane choice would be a loop that is in concentric circles. So go in concentric circles, that's Amperian loop C1, that's Amperian loop C2. You'll use as many Amperian loops as you need to complete the magnetic field profile everywhere in space. There are three regions, one inside the coax, one in between, and one outside. So choose 3 Amperian loops. This is just like choosing the appropriate number of Gaussian surfaces to get the job done. Now the left hand side of Ampere's law I dealt with the previous video, so I'll not go through it in great detail. I'll just give you some basic steps. So Ampere's law, first of all, is a statement that the circulation of the magnetic field around one of these Amperian loops, so I'll call it Ci, where I goes from 1 to 3, B dot ds is going to be mu naught times the current enclosed in the ith loop. So that's the law known as Ampere's law. The left hand side of Ampere's law can be reduced in this case, because even if it does have other components, you're only going to be getting a non-zero contribution from the tangential component bt, because that's the one that is parallel to the ds vector, or the tangential tangent to the curve ds. So then I can reduce the left hand side as follows. I can write this without the orientation sign as b tangential ds cosine 0 degrees. I can take b tangential outside because I know that it's going to be uniform as I go around by cylindrical symmetry. So I get bt as a function of r integral around the curve ci of ds, which everybody knows is just the circumference of a circle. So that's the abbreviated version of the reduction of the left hand side of Ampere's law. You should make sure to go and look at the full version in the previous video, where I gave you a really detailed derivation. All Amperian law loops have the same radius, little r, just like all Gaussian surfaces had the same floating radius, little r. Alright, now that we have finished the left hand side, and the left hand side, as I pointed out in the previous video, is going to be the same for all cylindrical symmetry, and this is a cylindrical wire. By the way, the coax cable is coming at you. So this is a cross section through the coax cable. The right hand side is mu naught times I enclosed. Let's focus on the right hand side in this video. I enclosed 1. First of all, barring that inner wire current, which I'll put in later, right now there is no current in the inner cavity. Okay, so I enclose 1. Actually, you know what? Let me put some mystery current here. I'll call this mystery current capital I. So it's just going to be capital I. And this is for 0 less than r less than a. Now the main calculation is I enclosed 2. How much is that going to be? That's going to be this portion only. Because you see, it's all the current enclosed between where the loop C2 is drawn and where the current starts. The current starts at A and the loop C2 is at value R. So this is given in terms of the current density. Current density is measured in amps per square meters. That's the units of current density. And it's always indicated by the symbol J. So the way current density has to be used is the following. It's the double integral over the surface S2, I'll explain what the surface S2 is, of J of R vector dot dA. Now, this is a dot product of two things, which means J of R is a vector and dA is a vector. The fact that dA is a vector is no stranger to you. You've seen that in Gauss's law too. But what is J of R as a vector? The vector direction of J of R comes from the direction of Benjamin Franklin or conventional current. So in this case, let's assume that the current in the coaxial part of this wire is coming out of the page. So I'll indicate that by drawing a few out of the page thingies here. If that is the case, then the dA vector is found as follows. Once you have the current direction decided, and once you have the loop direction decided, which in my case is almost always going to be counterclockwise, then you use another right-hand rule. And this right-hand rule goes as follows. There are, like I told you, a dozen right-hand rules in UP2, and they're all based on your thumb and fingers. So this time the right-hand rule goes as follows. Go in the direction of your C2 with your fingers. The thumb gives you the direction of the dA vector. Well, looks like everything is in place. J of R is outside the page, thumb is outside the page, so the dot product is just cosine of 0 degrees. So this is just going to be integral, double integral of the surface S2 of J of R times dA times cosine 0 degrees. Now what is the surface S2? The surface S2 is the one that bounds the curve. So the curve boundaries. So this curve C is this one, okay? But the surface is the one between the radius A and the radius R. So the way I'll play this is to write this as dA can be written as 2 pi r times dr. So this is going to be just the integral, single integral from A to R, J of R times 2 pi r dr. What I'm basically doing, for those who are well versed in multivariable calculus, this double integral is an integral over both r and theta. In writing 2 pi, I am doing the theta integral already. So now I'm just left with the r integral. So now it's just a calculus exercise. Let's put J of R, which I've given you, to be A times R. So it's integral A to R, A times R, times 2 pi r dr. So let me calculate that. 2 pi and A are all constants. That's integral r squared dr. Well, that's r cubed over 3. So this is 2 pi A over 3 r cubed minus A cubed. Done. Once I've found the current enclosed in the Amperian loop 2, the current enclosed by the entire Amperian entire thing. Oh, by the way, current enclosed by 2 should also include that I. So that's one of the reasons why I didn't want to put this I initially. So this is I enclosed 2 will include this I, because I is also enclosed in there. So we'll just add this I at the end. I enclosed 3 is going to be 2 pi A over 3, and here all you do is you put R equals B, because it's going all the way out, and then after B there's no current, so stop counting after that. So that's I enclosed 3. And once you have this, you have the full magnetic field profile. You'll set the left hand side equal to the right hand side, and you'll get the whole thing. Now, why did I put this inner coaxial cable current? Because that's how coaxial cables actually work. If you take out your TV cable or something and you're sick of TV, do the following experiment. Just take a hacksaw and cut it. You'll find a structure just like this. I used to have one laying around. I couldn't find it. Basically, a TV coaxial cable has an insulation that's made of plastic or something, and then there's a outer sheath of some thickness, and then there's some more insulation, and then there's an inner thing, inner wire. And the principle of the coaxial cable is that current is sent in opposite directions so that outside there is no magnetic field. So let's make that our purpose of this video. What should I be? So that the magnetic field for R bigger than B, the tangential magnetic field for R bigger than B is equal to 0. That means that this magnetic field won't interfere with the rest of your stereo system or video quality. Very important principle in electronics. Well, let's do that. For the magnetic field to be 0, by Ampere's law, the enclosed current has to be 0. And if you want the magnetic field to be 0 for R bigger than B, it's I enclosed 3 that has to be 0. So all we have to do is set this equal to 0. Set I enclosed 3 equal to 0. And voila, we have our current. The current is going to be negative 2 pi A over 3 B cubed minus A cubed. Let's just make sure that the units are good here. If the units of J are in amperes per meter squared, it means that the units of A must be amperes per meter cubed, because amperes per meter cubed times meters is amperes per meter squared. So the units are going to be amps per meter cubed times B cubed minus A cubed are going to be in meter cubes. So the meter cubes will cancel out and you'll get the answer in amps, which is the units of current indeed. So that's the coaxial portion of the current. Observe it's negative, which means that it's going to flow in the opposite direction. So in the coaxial cable, you're going to have the current flowing in this direction. Let's take a moment or two to plot the magnetic field everywhere in space. I will do that maybe right here because I have some white space. So let me plot the magnetic field. If I'm inside, I'm going to have, this one tells me that Bt times 2 pi r will be equal to mu naught I, which means that Bt will be mu naught I over 2 pi r. It's just like that of a wire, so it's going to be a 1 over r decay. What's going to be happen here in the middle? It's going to have that 1 over r decay from this term, but it's also going to have a quadratic growth term. Okay, so that's going to be a little bit of a, well, not exactly growth. The reason for that is because these two have opposite signs. So that's going to be a decay from below if this has a negative sign, and that's a growth, definitely. So it will make it go towards the r-axis. So let me just show you what's happening. I'll only look at values from 0 to infinity because our coordinate cannot be negative. Now the magnetic field less than A is going to be highly negative because the current is into the page. So I will plot the tangential magnetic field's magnitude and direction here. So it's going to asymptote because of the 1 over r thing, and then at A it's going to look like that. Now between A and B, magic has to happen. Normally it would have gone on like this, but that cannot happen. It needs to be forced into the origin, and that can be done by just freehand drawing. And then after that, it just flat lines. So that's your magnetic field. 1 over r decay, a little bit of growth, polynomial growth of r squared type growth, along with a small component of decay again because of the r 1 over r here, but we're not going to look at those fine details. And then that's the general profile of the magnetic field.